Hey y'all. Today we're going to look at something called the common ion effect, which really is a application of the Le Chatelier principle that we've already talked about. So what we're going to do is we're going to start by looking at how it applies in a conceptual level, and then we're going to apply it somewhat mathematically as we go forward. We're going to jump right in with a look at a particle diagram here. In this case, we are dealing with a saturated solution of silver chloride. We know it's saturated because there is solid at the bottom and because I'm telling you it's saturated. Remembering that a saturated solution means that the solution is already at an equilibrium position between the solid and the ions. Let's think about what might happen if we were to add something where one of the ions was a component, for instance, hydrochloric acid. If we add hydrochloric acid, which is a strong acid, and it fully dissociates, it dissociates into H plus and Cl minus. Cl minus is a common ion with silver chloride, AgCl. So what we're doing here is we're adding a common ion through the addition of hydrochloric acid. Now, in a conceptual level, let's remember that the process of going in the reverse here is due to a collision between a silver ion, Ag+, and a chloride ion, Cl-. So if we add more Cl- ions, we are going to get more collisions, which means the reaction in the reverse direction will have sped up initially. What that's going to do is create more solid salt. But at the same time, it's actually going to remove some of the Ag+ ions from the solution. So what's going on here is by adding a common ion, we're shifting the reaction, in this case to the left, towards the solid, because the common ion is going to speed up the reaction in the reverse direction. Now that we've looked at it from a conceptual frame point, let's now think of this from a mathematical frame point. We've already talked a lot about Q and K, and this applies here as well. When we increase the concentration of one of the products, we are increasing the value of Q. This makes the value of Q greater than K, because remember, we started where Q was equal to K. It started as a saturated solution. So by increasing the Q, we're going to make it larger than K, which is going to increase the rate of the reaction in the reverse, shifting the reaction in the reverse direction, thus creating more of our precipitate. By shifting the reaction towards the solid, what that means is that in the presence of a common ion, solubility decreases, because less of that solid will be considered to have dissociated. Let's take a look at this using a rice table. So what I'm going to do here is I'm going to set up a rice table to show you exactly how much the solubility is going to decrease as a result of a common ion. One of the challenges of rice tables with solubility equilibrium is that the reactant is a solid, and we know that we don't include solid species in our equilibrium expressions. We've already talked about how to ignore them in our equilibrium expressions, but in a rice table, what I'm going to do is I'm just going to say some and less so that it's a kind of a placeholder. The more important components here are going to be my initial amounts of both the Ag+ ion and the Cl- ion. So what I'm going to do first is we're going to solve assuming we had no common ion present. So both the Ag+ and Cl- are going to start at 0. They're going to both change by x because their coefficients are 1 each. And as a result, at equilibrium, we're going to see them both equal x. This means our Ksp is equal to s squared. The Ksp is 1.6 times 10 to the negative 10th, which means that the square root of my Ksp is going to be equal to S, our solubility, and that, without a common ion present, is 1.3 times 10 to the negative 5th. So the solubility of this compound, silver chloride, without a common ion present, is going to be with an exponent of 10 to the negative 5th. Okay, so that's the thing to keep in mind here. Now let's look at what happens when we add a common ion. The key to a common ion is what we're going to change is the initial amount of our common ion. In this case, it's going to be the Cl-. Because the solution of HCl, which is a strong acid, is 0.02 molar, that means what I'm doing is I'm adding 0.02 molar Cl- ions. Okay, remember, strong acids fully dissociate. So with 0.02 molar Cl- ions, it is still going to increase by x. So if we look at my rice table as I've augmented it here, you're going to see that my initial for the Ag+ is 0. The initial for the Cl- is equal to the amount of the common ion added, in this case due to it being in a solution of HCl. That means at equilibrium, the Ag+ is going to equal x, And the Cl minus is going to equal x plus 0.02, or 0.02 plus x. Here's a trick for solubility equilibrium. The difference between 0.02 and 0.02 plus x is negligible. It doesn't make enough of a difference, and as a result, we are going to ignore the plus x in the 0.02. And so what we're going to assume is that the concentration of Cl minus at equilibrium is equal to 0.02. The reason we can do this is because the x in solubility equilibrium is always going to be small enough to be able to ignore when we're adding it to the amount of common ion. This is a really important thing to remember. We're not ignoring the x in the Ag plus because it's just x, and we're going to be using that as a multiple, not adding or subtracting. So as we solve this problem now with a common ion, what we're going to realize is that in my KSP expression, the KSP hasn't changed, right? The value of KSP is still 1.6 times 10 to the negative 10th, but we've replaced the concentration of Cl minus with the concentration of our common ion, Cl minus. So we're still solving for S in this case, the concentration of Ag plus, but the concentration of Cl minus is going to be 0.02. When we solve for the S value now, what we find is that S in this situation is equal to 8 times 10 to the negative 9th. If we remember, without the common ion present, the exponent was 10 to the negative 5th. Now with the common ion present, we have decreased our solubility of AgCl by 10 to the 4th. Now that's a big difference to change it by 10,000 times just by adding a 0.02 concentration of a common ion. All right, I'm going to have you all do a practice problem now. I want you to find the molar solubility of lead-2 chloride in a solution that already has 0.1 molar potassium chloride. The KSP of lead-2 chloride, 1.7 times 10 to the negative 5th. All right, so go ahead and solve this problem. Take a second, pause the video if you need to, solve this problem, and I'll help you through it when we get back. All right, so let's go ahead and solve it. Here we have lead-2 chloride. Again, the solid, we're going to say some and less just as a placeholder. But the key factor here is that with the lead-2 plus ion and the Cl minus ion, what we're going to do is we're going to replace the Cl minus ion with the concentration of the chloride in the potassium chloride solution, so the 0.1. The lead is going to increase by a factor of x, but the chloride is increased by a factor of 2x, okay, because there's two Cl minuses. So at equilibrium, the concentration of lead is going to be equal to x, and the concentration of chloride ion is going to equal 0.1 plus 2x. That being said, we can still ignore the x. So we're going to ignore the 2x that we're adding there. So as a result, at equilibrium, the concentration of lead is going to equal x, and the concentration of chloride is simply going to equal 0.1. We take these values and we plug them into our equilibrium expression, our KSP, which is equal to the concentration of lead ion times the concentration of Cl minus ion squared. Plug them in. That means it's going to be 0.1 squared times the concentration of lead, so S, is equal to our KSP. We solve for S. S in this case is equal to 1.7 times 10 to the negative 3rd moles per liter. That means with the common ion of chloride present in this solution, the solubility of lead-2 chloride would be equal to 1.7 times 10 to the negative 3 moles per liter. So that wraps up today's video. Let's do a quick recap. We started today by looking at how a common ion impacts the solubility of any ionic compound. Remember, the presence of a common ion will always decrease the solubility of a compound. And the reason is because we increase our Q relative to our K, and we shift the entire reaction to the left towards the reactants, which, remember, is the solid. So our solubility decreases. Then what we did was we solved for the equilibrium concentration and solubility of a salt, assuming a common ion is present. In this situation, we saw mathematically how much a common ion decreases the solubility of a compound. So as we go forward, keep in mind common ions are simply an application of Q versus K. We can do it conceptually and we can do it mathematically. This video was written, directed, edited, and produced by Lucy Park. Thank you all for watching it. Hope you enjoyed it, and I'll see you in the next one.